Professor Zhang, who was supposed to be here today, but he couldn't make it because of an unexpected commitment, and therefore we will have Professor Gong Yan to replace him, who will talk about the China Space Station telescope, as I just mentioned, and at the end of the talk we'll answer the question. So thank you very much, Professor Gong, for accepting our last-minute invitation and for giving the lecture today. You can see him in the camera, and in the camera you can also see Professor Wingwen Ip, who is the Executive Director of ISSI-BJ, and I'm Laura. If you have attended our previous webinars, you know me. I'm the PR and editorial manager at ISSI-BJ. I'm gonna say, as usual, a couple of questions about the institute, and then I will ask Professor Ip to introduce Professor Gong to the audience with you today. So ISSI-BJ, the International Space Science Institute Beijing, is the partner institute of ISSI in Bern, so the International Space Science Institute in Bern, Switzerland, and it was established in 2013 thanks to the collaboration between ISSI and the National Space Science Center of the Chinese Academy of Sciences. Since then, we've dedicated our time and energies to the advancement of space science studies. We cover a wide array of disciplines: space physics, solar physics, and so on. And we do it in a multidisciplinary way. Therefore, we create groups of scientists and experts and researchers to come to our premises and work on the research projects. We have organized workshops, forums, we have some international teams, working groups, and so on. There used to be, of course, offline events. Since the start of the pandemic, we've turned to online events. And thanks to the energy and enthusiasm of Professor Ip, we started last year in September the On Things to Come webinar series. So the current webinar is part of it, that aims to introduce ongoing and future space missions. And as I just mentioned, we have today Professor Gong to talk about the China Space Station telescope. As you can hear, the language of these lectures is English, but we also have a webinar series in Chinese, which is called 1001 Space Nights, 天方夜谭 in Chinese, that takes place every Monday, one Monday per month, and the next one is going to be next Monday. In this webinar series, we introduce the work and achievements of Chinese female scientists, and I will say maybe a bit more at the end of this webinar. Without further ado, I would like to ask Professor Ip to introduce Professor Gong, and thank you very much once again for being here.
Yeah, thank you, Lola. Good afternoon in Beijing, in Taiwan, and good morning or good early afternoon in Europe. And welcome to this webinar, which will be given by Professor Yang Gong of NAOC, the National Astronomical Observatory of China. And the topic will be on Chinese Survey Space Telescope, CSST for short. I think some of you might have heard this project for quite some time, which will be, as you will hear from Professor Gong, will be launched in 2024. But then let me introduce you Professor Gong a little bit first. He got his undergraduate in University Jinan. I suppose Jinan. I suppose later I will confirm him. It's in Shandong and he did his PhD study at the National Astronomical Observatory, China. And after his PhD, he went to UC Irvine to do her postdoc, and he returned to NAOC in 2015, and to continue his career as a professor now. And his research field is a cosmologist, in fact a theoretician. So I'm very interested to know how he got involved in this very heavy instrumentation. He will have a lot to explain to us. And he worked on dark matter, dark energy, and then he write papers like cosmological constraints on ultralight Hessian fields. But I think today he will tell us about what this CSST could do. Professor Gong, please.
Okay. Thanks, Professor Yip, and also Laura. And hi, everyone. And I'm Yan Gong from NAOC. So as Laura mentioned, Professor Zhang has a emergency meeting this afternoon. So he asked me to give this talk yesterday, and I'm actually mainly working on the CST science. But in this talk, as you will see, many slides is about the instrument. Actually not my familiar area. But fortunately, I have support here. I have support from Professor Zhang's group and a few researchers from his group, like Dr. Xianming Meng and Dr. Xiang Fu. They definitely know more details of instruments and can answer relative questions. Okay, so let's start our talk. The title is Chinese Surface-Based Telescope, and it is also known as the China Space Station Telescope. Although the full name are different, but the abbreviated name, CSST, is the same. This is the overview of the CST. The CST is a 2-meter aperture space telescope in the same orbit as the China Manned Space Station, and it is serviceable while docking with the station. And also the CST currently has 5 instruments. The survey camera is here, and the survey camera is the main instrument of the CST, and it will detect the evolution of our universe, and also the formation and evolution of the large-scale structure, and it will detect and probe the properties of dark matter and dark energy, also tests modified gravity and other things about cosmology. And the next one is Terahertz Receiver. Terahertz Receiver will probe the emission lines of atomic and molecular gas or clouds. And another one is Multichannel Imager, MCI. The MCI will focus on the deep fields. It's very deep. It will study like the Shuangnan thing, and also detect the type 1a supernovae, and it can also perform calibration for the survey camera. The fourth one is the integral field spectrograph, the IFS. The IFS will probe the galaxies and the massive black holes, and it will study the galaxy formation and also the properties of massive black holes. The last one is called CoPlanet Imaging Chronograph, CPIC, is right here. The CPIC will detect the exoplanets and study the exoplanet physics. So this is the current 5 instrument of the CSST. For the mission part, CST will perform a wide area multi-band imaging and slitless spectroscopic survey in about 7 years. Besides, it also will perform a deep field survey. And the other key program and guest observer program will take about more than 2 years. So for the CST, totally it is about 10 years mission. And this picture just shows the CST will dock with the space station and for maintenance. The next one is project timeline. As early as 2010, the CST mission concept and definition is determined. And at that time, we only have two instruments, the survey camera and the Terahertz Receiver. And 3 years later, and the whole mission was approved. And 1 year later, the CST free flying design is confirmed. And in 2018, 3 new instruments were added to the CST, the MCI-IFS and CPIC. And in 2019, the data reduction system design is determined, and also the final design of optical assembly, survey camera, and the Terahertz receiver were confirmed here. And last year, 2020, we formed a science committee for the CST, and also we set up 4 science centers. And the data reduction system and research projects were also approved in this year. In addition, the final design of the other 3 instruments, MCI, IFS, and CPIC, were confirmed. And from this year to 2023, this about 3 or 4 years, the qualification model and the flight model will be studied and produced. And so, as expected, we plan to launch the CST in 2024. So during all of this, about 10 years, we actually have held many meetings and workshops to discuss the science instruments and also data processing, etc. For example, in 2017, we invited the directors of ISST, Euclid, and also W-FIRST or Raman telescope, and also other senior scientists from all over the world to have a workshop to discuss CST science, data processing, and instruments. And we plan to have this kind of meeting every year or every 2 years in the future. So for the organizational structure of science work, so currently the CST science is mainly funded by the Chinese Manned Space Office, and it is administered by the Space Application System. We also formed a science committee last year to make big decisions of science. And the research management and organization right now, we have a joint science center and also 4 science centers. The joint science center actually can provide administration supports for these 4 science centers. These 4 science centers include Peking University Science Center, NAOC Science Center, and Yangtze River Delta Science Center, and also the Greater Bay Science Center, including Guangdong Province and also Hong Kong and Macau. So this is a very large science team for the CST. So for the science committee, currently the convener is Professor Li Donggu. He is actually also the chief expert of the space science. And also the committee has 4 vice chairs, Professor Jin Chang, Jiawen Han, Yi Jingpeng, and Louis Ho. Besides, the members include nearly 20 senior scientists here, including Professor Zhang. besides the project scientist team was also set up this year. It is led by Professor Zhang. For the survey specs, the CSST will perform both wide survey and deep survey. For the wide surveys, it has photometric imaging and also slitless spectroscopic survey. The wide survey will cover about 17,500 square meters, and the wavelength coverage is from 255 to 1,000 nanometer. And the number of filters is greater than 6. Currently, the CSST has 7 filters. And the average magnitude limit is about 25.5 magnitude. This is for the 5 sigma point sources. And for the slitless spectroscopic survey, it will cover the same area and the same wavelength range, but it has less bands. It only has 3 bands, and the spectral resolution is about 200, and the magnitude limit is about 22 to 23. Besides the wide survey, the CSST also has 400 square degree deep survey. And the deep survey also has both imaging and spectroscopic surveys. And the deep survey is at least 1 magnitude deeper than the wide survey. Besides, the wide survey and the deep survey are actually performed by the survey camera. And for the MCI, it can also will also perform a super deep survey. The super deep survey only covers about 300 square arcs-minute, and it can simultaneously observe in 3 bands. And the V-band magnitude can reach 30 magnitude. It's very deep. So this picture shows wide survey. As you see, the blue region is wide survey scar area, and the red dots are the deep survey area. But the deep fields will be finalized later. This is just for demo. For the CSST science, it has actually from cosmology to the solar system, all of these important astronomical fields. But cosmology is obviously the most important science for the CSST. And we will study the properties of dark energy and dark matter, and also test gravity theory, and also explore the evolution of large-scale structure, explore the properties of neutrinos, and also primordial non-Gaussianity. And for the galaxy and AGNs, we will construct maybe the largest AGN samples, and also study the galaxy formation and evolution. And for the Milky Way science, we will detect the fine structure of Milky Way and study its satellites, and also the nearby galaxies, the interactions, the dust extinction. And for the stellar science, we will study the formation of stars, study dwarf stars, metal poor stars. And for the solar system, the CSST will focus on the high inclination region, and to detect like small objects in the solar system. And for the astrometry, the CSST will improve the accuracy and observe the star clusters. So the next is telescope specs. The CSST has an aperture of 2 meters, and focal plane length is 28 meters, and field of view is 1.1 square degree. So this is almost 300 times larger than the HST field of view. It's a quite large field of view. And the wavelength coverage, the wavelength coverage is from 0.255 to 1 microns. And the CST also have a near-infrared unit for testing purpose, and its wavelength coverage comes from 0.9 to 1.7 microns. And the image quality is also very high for the CST. This RE80 is 80% energy concentration radius. This radius is encircling about 80% energy over objects. So for the CST, this radius should no larger than 0.13 arcsec, and the whole system should not larger than 0.15 arcsecond. Also, this is the filter throughput. The filter throughput must be greater than 65%. And we also have some pointing accuracy, stability, jitter, slew, all of these parameters. I will neglect these details. Okay, this is the system design. The CST is actually a cooktop of X 3 meter anastigmatic system. So it is also serviceable while docking with China Space Station. And for the slew and line of sight ruling, and the CST has control momentum gyro and steward platform plus fast steering mirrors, and also plus the vibration controller. So besides these three instruments, MCR, IFS, and CPIC, can observe in the meantime, but it is limited by power actually. But in principle, all of these three can observe in the meantime. This picture shows the structure of the telescope. You can see there are 6 slots here. The CPIC will take these 2 slots, and MCR and IFS will take this big one, and also the survey camera will take the other side, this slot, and the terahertz will take this small one. And these are the 5 instruments, and we also have an open slot for the future use. Because CST can dock with their space station. So in the future, the technauts can probably add another instrument, interesting instruments here. So this is MCR, this is IFS, CPIC, and the Terahertz Receiver. The next is optical design. Optical design. So the CST is a 2-meter aperture telescope, and the mirror is made of silicon carbon. It is also of XTMA. So this picture shows designed PSF at corner. So the requirements is pretty high actually. Is like the radius should the energy concentration radius, it should be less than 0.15 arcsecond at 630 nanometer. But in the simulation, we actually find the PSF plus jitter effect, and we find it can be even little bit better So we find that this radius even is less than 0.13 arcsecond, and the pixel size is about 0.074 arcsecond. And we also did some tests for the wavefront errors and also the ellipticity. So this is the survey camera. This is the whole survey camera here, and also shows the different parts of the survey camera. For example, this is the shutter, the imaging filters, the gratings. This is the focal plane, and also we have a wavefront sensor located here, and also the near-infrared unit is here for testing purpose. And we also have a fan guidance sensor right here. Also has ELAX at the bottom, and also the cryo cooler at the back of the camera. So right now the fabrication is in progress. This is some pictures, the tertiary mirror, primary mirror, and also we did some tests for the wavefront errors of the primary mirror. So currently the error is about 15 nanometer. Also this is a comparison with the other objects. Here we have 4 objects: CST, Euclid, Raman or W first. This is Rubin or LSST. The first 3 are the space-based telescope, and the last one is the ground-based telescope located in Chile. For comparison, we can see that for the CSST, it has a very large field of view for the space telescope. It's larger than Euclid and Raman. Of course, it is smaller than the LSST because it is a ground-based telescope which can be very large. So the energy concentration radius for the CST is about 0.15. It is very small compared to Euclid and the Raman telescope and also the LST. And the number of pixels is also quite a lot. It is only a little bit less than the LST, but it's much larger than the other 2 space telescopes. And the survey area is also quite large and comparable to the Euclid and Rubin LST. And for the wavelength coverage, the CST has a unique coverage in the UV band, and is from near UV to the near infrared bands. We can cover all of this wavelength range. On the other hand, for the Euclid, it only has one band, one visible band here from 550 to 920. And also for the Raman or W first, it only has near-infrared bands. For the Rubin ground-based telescope, it also only has visible bands. But only the CST has a near UV band here. And also the CT has the most number of filters greater than 6. Right now it is 7 filters. This is very useful for the photometric redshift calibration for the main science. Besides all of this, CST, this is the PSF for the CST. You can see that the CST PSF is quite regular. It's very Gaussian-like PSF. For comparison, here is HST and here is Euclid. And also the CST has a very small energy concentration radius. All of these advantages can make CSST can make CST obtain a superb image quality. So it has advantage for lensing studies. And gravitational lensing, especially the weak lensing, is the most important scientific targets for the CST to detect the evolution of the universe and also the properties of dark matter and dark energy. For the filters and limiting magnitudes, as I mentioned, the CST has 7 filters for photometric imaging survey. These are the 7 filters, and this is a detector quantum efficiency. So we found that the CST, the WET survey has exposure time. The exposure time is about is 2 times 150 seconds, and for the deep survey it is 8 times 250 seconds. And for the WET surveys, magnitude limit is averagely about 25 to 26, and for the deep survey it is at least 1 magnitude deeper. Besides, for the NUV and wideband, we actually has 4 exposures. The other band has 2 exposures. And this is a vendor design filter curve. It is quite similar to these curves. This picture shows the wavelength versus the 5 sigma point source threshold. The stars are the CST. You can see that the magnitude limit of CST is quite close to the Euclid, but the LSST and the W first will go deeper. But W first has smaller scar coverage. And we also did some work for the photometric redshift estimation. And photometric redshift is pretty important in the weak lensing surveys, and it is one of the main systematics in weak lensing. So for the CST, actually this work has been done by one of my students, Haoye, and here we are using a cosmos field, as a catalog, and considering the CST instrumental and observational effects, we generate the CST mock catalogs from this Cosmos catalog. And we found that the redshift distribution of the galaxy observed by the CST is peaked around redshift 0.6 or 0.7. And also it can extend to redshift 4. And the magnitude limit is about a little bit deeper than 25, which is consistent with our estimation about. So for a very high signal-to-noise ratio sample, this sample has the signal-to-noise ratio greater than 10, and the CST will have galaxy density about 17.5 per squared arc minute, and this is corresponding to a photometric accuracy about 0.024. This is actually accurate. This is actually very accurate. And if we relax the accuracy, the photometric photo-Z accuracy to 0.05, then we will have more galaxy density, about 30 per squared arc minute. And next one is the gratings and its limiting magnitudes. So as I mentioned, the CT has 3 spectroscopic bands, the GU, GV, and GR, the 3 bands. And the coverage, the wavelength coverage is the same as photometric imaging survey. And also the sky coverage is also the same. But for the exposure time, it is for the wide survey, it's about 4 times 150 seconds. And the magnitude limit for the 3 band is about 23. And for the deep survey, deep spectroscopic survey, the exposure time is 16 times 250 seconds. And the magnitude limit is 1 meg deeper. And the red panel shows the example of AGN observed at redshift about 5, and the magnitude is I equals 18, and we dim it to I equals 22. And also considering the beam effect, we can obtain the low resolution spectrum, and we can also extract the spectrum from these observations. So this proves that for the CSST survey, we can. It is very powerful to extract the spectrum from the AGN sample. And it has advantage to detect and confirm the AGNs. Besides, we are also checking against HST Pair Survey. This survey is covering about 120. This survey contains about 120 galaxies per square arc minute. And the spectral resolution is lower than the CST, but the magnitude limit is much higher. It's about like 28. You can see that for the CST, if the signal to noise ratio is greater than 20, we find that the CST emission line galaxy can be about 1.5 per squared arc minute. And totally, we will have 100 million spectra from the emission line galaxies. This is quite a large sample. And the bottom panel shows the magnitude, shows like the number of galaxies as a function of redshifts for different magnitude limits. For the CST, it is about I bands, about 23 magnitude, this blue curve. So we can see that it will has a peak around 0.5 or 0.4 and can extend to 1.5 or 2. And we also check another other catalogs like Z Cosmos catalog. We have the similar result. All right, so next is the tiling of the sky. This is the focal plane of the CST. The upper and the bottom are the gratings, and the inner and center region is for the photometric imaging filters. So when tiling the sky, for example, this 2U band, 2U filters, like this, and it will tiling the sky as this progress. And for each shape, the overlapping region is about 10 seconds. And also, if one chip covers the whole sky, all other chips will also cover the whole sky. The number of same type filter is equal to the number of visits. For example, for U-band, we have 2 filters, and that means we will, for the same region of sky, we will have 2 visits. But like for the NUV or the Y bands, we have 4 filters. So that means we will have 4 visits for the same patch of sky. Next is operation simulations. We did some simulations to optimize the survey coverage. So this is a 10-year coverage in the simulation. For the wet survey, it's about 17,500 square degree. For the deep survey, it's about 400 degree. The most constraining factor to affect this operation simulation is the sun and the earth. Also we can say that the galactic plane and the ecliptic plane can also be observed in the survey. And the red panel shows the top panel is for the wet survey, and the lower panel is for the deep survey. And the x-axis is the time in year, and the y-axis is for the sky coverage area. The red line, the red curve is for covered by any filter. And the blue one is for all filters at least covered once. And the green is for all filters complete. So you can see for the wet survey as the year 10, it will cover the whole 17,500 area. Besides the wide and deep survey, we also plan to perform a ultra deep fields, but this is the demo and it is not fully determined at the current stage. The plan is that we will observe ultra deep fields in this square region, and this is the inside out sky coverage strategy, and the total exposure time is 60 times 250 seconds to cover about 9 square degrees this square. And these dots, this red dots is actually for the normal deep survey of the CST, and this blue region is actually for the wet survey CST. And this is year versus area completeness. So we can see that for this ultra deep survey, it can be completed in the first 3 years. So the magnitude limit of this ultra deep field can reach about 28 magnitude. So it is quite deep field. And the bottom panel shows number of visits for the 7 filters. For the NUV and Y, we have 120 visits, and for the other filters, we just have 60 number of visits. So above is about the survey camera, and we also have a terahertz receiver. The terahertz receiver, the frequency coverage is about 0.41 to 0.51 terahertz, and the bandwidth is greater than 2 gigahertz, and the resolution is larger than 100 kilohertz. Sensitivity is smaller than 150 millikelvin. The cryo cooling is greater than 10 milliwatt. So in the frequency range of the terahertz receiver, it will search for new atomic and molecular emission lines, and also studies the physical and chemical process of these gas and clouds. And also it is complementary with Herschel telescope. Besides, the terahertz receiver will try to probe carbon cycle. For example, the C1 at the frequency 492 gigahertz, and it will study the evolution of molecular clouds in early stage, and also studies filamentary structure in the molecular clouds. And for the multi-channel imagers, MCI, MCI has 3 channels, and all the 3 channels can simultaneously perform the observation, the U band, V band, and I band. And also it has 30 filters in the MCI. And the detector is a 9K by 9K detector, and the pixel size is about 0.05 arcseconds. The field of view is large, is greater than 7.5 by 7.5 arcminute. And for HST standards, MCI actually has high precision photometry. So also it can be a calibration. It can perform calibration for the survey camera, for the main survey camera. For example, this is a field. This is a field of view of the MCI. It will perform a super deep field survey. The super deep field survey actually contains 5 fields, and totally survey area is about 300 square arcminute, and the V band magnitude can reach 30, so it is super deep. And the survey area is also 30 times greater than the Hubble telescope XDF field. For XDF field is this small, and this is a field of view. This is the field of view as MCI. MCI will have 5 fields, and totally 300 square arcminutes. And the MCI will detect high redshift supernovae, about like 100 supernovae at redshifts greater than 1 can be detected by the MCI, and we can use this type 1 supernovae to explore the expansion history of our universe, and also to prove the properties of dark energy. And also it can be a completeness, it can check the completeness of the galaxies used for wavelengthing and galaxy clustering in the survey camera, in the main surveys. And also it can perform science like galaxy and black hole co-evolution and other interesting science. And the next one is the integral field spectrograph, IFS. IFS can take spectra of different parts of the source simultaneously, and finally we can get both image and the spectrum of object, so we can get a 3D data cube of an object. So for the IFS, the spectral resolution is about 0.2 arcseconds, and the spatial elements is 30 by 30, and field of view is actually small compared to the survey camera and MCI. It is only 6 by 6 arcseconds, and the fading factors is 100%. The wavelength coverage is also large, from 0.35 to 1 microns. Coverage is large, and the spectral resolution is high. It is greater than 1000, and it is 0.1575 nanometer per pixel. So for the IFS, it can probe the supermassive black holes and its surroundings, like measure the black hole masses, fading and the feedback of black holes, the star clusters and star formation around these black holes, and also TDEs. Also, it can explore the star formation of galaxies and other science. For the CoPlanet imaging chronograph, the CPIC, of course, it will probe and detect exoplanet For example, it has a wavelength coverage from 0.6 to 0.9 microns, and the bandwidth is from 3 to 10%, and field of view is 2.5 by 2.5 arcsec. And the contrast is quite high, is 10 to minus 8 or better. From this plot, you can see that this corresponding to like Jupiter-like planets or CoPlanet here. So this is the optical layout of the CPIC, and also they did some vacuum chamber tests, and they found that the contrast can even reach 10 to minus 9. So this is very high contrast. Above are the instruments of the CST, and using all of these 5 instruments, we can perform many interesting sciences. The most important one for the CST is the cosmology. First is to explore the dark energy and the properties of dark energy and dark matter. And the most important scientific target is the weak gravitational lensing. And we can measure the weak lensing very well, and then we can extract the information of expansion history of our universe and the evolution of a large-scale structure to explore the dark matter and dark energy, and testing gravity theory and measuring Hubble constants, etc. And also we can use the slateless spectroscopic surveys to mapping 3D galaxy distribution. And then we will the galaxies can be seen as tracers of dark matter. So then we can map the matter distribution of the universe, and then we can prove the large-scale structure of the universe. And also our team has did some predictions for the constraints on the dark matter and dark energy, like using the weak lensing and the galaxy clustering surveys and the joint surveys of these two surveys, the weak lensing RSD and also galaxy lensing surveys. And we can see that the constraints on the dark matter and dark energy accuracy can reach about 3 and 5% respectively. This is very accurate, and it is almost 1 order of magnitude higher than the current measurements. So it can detect the properties of dark matter and dark energy the properties very accurately. And besides the cosmology, and we can also explore the galaxy and AGNs, and the CST will contrast probably the largest AGN samples, and also it will study the hazy galaxies and properties of AGNs. And for the nearby universe and the stars, the CST will illustrating the structure and the evolution of our Milky Way, and also the nearby galaxies, like the interaction between these galaxies and other effects. And also it will study the stellar physics, formation and evolution of different types of stars. And also it will improve the accuracy of astrometry, and also detect the solar system small bodies in high inclination, and also will detect many transient objects like the magnetic, like the type 1 supernova, and gravitational, the objects of gravitational wave. Besides, exoplanets can be also detected by the CPIC of the CST, and it will prove the actual planets and also study the physics of these planets. Okay, in short, the CST is a powerful telescope to explore our universe. Okay, thank you. I'll stop there.
Yeah, thank you very much, Professor Gong.
Thank you very much, Professor Gong. Yes, thank you very much for the outstanding presentation. And as mentioned by Professor Gong at the beginning of the talk, in case there are any questions about the instruments, and we also have the help of Dr. Meng, who is on the call too, in the meeting too, who will also step in to answer the questions. So I see already 3 questions in the chat box. You feel free to send more also on Bilibili for our audience on Bilibili. And I think we can start with the first one, which says, the point spread function of CSST looks very good. Is it from real measurements or simulation?
Yeah, this is actually from a simulation, but it is all pixelized. Yeah. And in the simulation, they have considered as many effects as they can. But of course, it could be worse. But currently, we found it is still very, very good.
Okay, thank you very much. Next question. The limiting magnitude in deep field is exciting. It can catch TNOs of 100 kilometers in size out to about 100 astronomical units. Are the field directions already defined? Is there any of that close to the ecliptic where there are more TNOs?
You mean the survey area, right?
Sorry?
I think that the question is that why not the Professor Xiangguang? Can you ask him? I mean, you can unmute yourself and ask the question yourself.
If Professor Chang wants, I can turn on your microphone. If he wants, you can drop maybe a message. I don't want to do it without making sure you want to turn on your microphone, but if you want, that is possible. You can just drop a message in the chat box. Shall we maybe then go to the next question? Okay, he's not able to turn on his microphone now. Okay. Professor Gong, you can also see eventually the question is in the chat box, in case you want to take a look and read it.
Let me see the limiting you mean the limiting magnitude of in deep field? It can catch other field.
But I think that
it's not defined yet, as far as I know. This is just a concept, and also we actually have a team is working on that. But I don't know that. Sorry, I don't know the details. Yeah, but there is a team working on the solar system. Right.
Thank you.
Yeah, I think that for a deep field, I have a question, Professor Gong. For a deep field, how do you do it? You do it from orbit to orbit, or from time to time? I mean, separate by a month, or separate by a year, because then because Professor Zhang is interested in the moving object, in the TNO, so it would be moving in the between, even though the movement is small.
Right. So as far as I know, we will do it separately, but the separation time is not quite regular. Maybe at the beginning of the mission, you can see this coverage as a bottom panel. This is for the deep survey, and at first the deep survey probably will have no coverage, but at the late years, it can be be greater, can be large, very slow, and to reach the final 400 square degree.
Yeah. Yeah. Okay. Good. Yeah. So it would be covering, several years. So it's
Thank
not.
you.
Yeah. Because it will have 8 explorers for the deep field, so the for the 8 number of visits, and the separation time may be not regular, maybe like years or months, yeah, something like that.
We have another question. I see in the chat box. For weak lensing measurements, can CSST reach beyond Z2?
You mean the source, the weak lensing source? I think yes. If you look at the redshift distribution here, it can actually reach to redshift 4. And at redshift 2, we still have a lot of galaxies. Although the peak is around redshift 0.6 or 0.7, but at 4, we still have many galaxies.
So how is the CSST compared to Euclid then?
Euclid, because Euclid has infrared bands. It's let's see here. For the Euclid, the coverage can be can reach like 2 micron. Yeah, so Euclid will have more galaxies at high redshift. Yeah.
If anyone has any other questions, also very sorry. I don't see any more questions here in the chat box or on Bilibili. If you want to ask questions to Professor Gong, this is your moment. In the meanwhile, I would like to mention that you mentioned the Euclid mission, and we had a lecture with Professor René Loreis. I remember the pronunciation is probably not correct. It was last week, and we have already published the recording. So as it will happen this week with this talk, every time we have our On Things to Come webinars, we record them and then we publish the recording, the video on our website, on YouTube and Bilibili. So you can also, you can always refer to our website to watch the previous webinars. And again, also the webinar of today, in case you missed it or you couldn't hear the full lecture, it will be published tomorrow or the day after on our website as usual. Professor Ip, do you have any more questions for Professor Gong, maybe?
I think that I wish him good luck,
Yes.
Yeah. A successful launch and operation, yes.
Yeah, this is a very large project, and it's many scientists to join, and we hope we can success and with all our efforts. Yeah.
Perfect.
Yes, thank you so much.
And, sorry, thank you very much. Yes, I would like to remind everyone, we're short on time, but I would like to remind everyone we will have a talk also next week, next Wednesday, the 14th of July. It will be with Tomoko Arai on the Destiny Plus mission of JAXA. And then we will have on the 21st of July with Michael Kuppers, we will have a lecture on the ESA-HERA mission. So we will have a couple of other talks before ISSI-BJ takes a break around the end of July, and hope to see you there. Thank you very much once again, Professor Gong, for stepping in last minute for the great talk, and also for Professor Meng to be online and making himself available for the talk. Thank you very much once again, and wish you a good evening for the ones on this part of the world. Bye-bye.
Bye-bye.
Okay.
Thank you so much.
Bye. Thank you for your work.